Okay, going through a chemistry A-level question here. Let's get into it. This question is about biofuels. A palmitic acid can be made by hydrolysis of the triester in palm oil under acidic conditions. Palmitic acid can be used as a biofuel. Complete the equation for the hydrolysis of the triester in palm oil under acidic conditions. So here is our triester. We've got acidic conditions, you see by the hydrogen ions there on the arrow, and we've got three water molecules. So we're really looking at hydrolysis of this bond. You're just looking to hydrolyze this ester bond and show the products. And of course, for those biologists, you know the product is going to be a glycerol molecule, propan 1,2,3 triol, IUPAC name, and it's going to be hydrolyzed here. So the first question literally says complete the equation. So they just want us to write the products out. So what are going to be the products? Well, first of all, we're going to make a molecule of glycerol. So we're just going to write the formula like this: CH2, which is the first bit there. You're going to attach an OH there. So you put in brackets the OH to show it's attached to this carbon and not to the carbon after it. Then we've got CHOH. Again, the brackets show which carbon it's attached to and not the one after it. And then for the last one, we can just put CH2OH, and we don't need brackets because there's no more atoms following. So the OH must be attached to the carbon before it. Okay, so that's a glycerol molecule is formed. What else do you get? Well, you get three fatty acids. Okay, and I've just circled one of them. What you've got to do is redraw that out. You get three lots of palmitic acid. So you're adding the OH bond to the glycerol, but of the three water molecules, three hydrogen ions add to the COO to make the carboxylic acid group. So we're going to get CH3, CH2 with a 14, COO, and of course that would be negative, and you get that positive hydrogen ion that snapped off when the water was involved in the hydrolysis, and that hydrogen ion joins to that carboxylate group and forms a carboxylic acid. Like that, and you're going to have three of them. Okay, 8.2. Palmitic acid burns in air. In a calorimetry experiment, combustion of 387 milligrams of palmitic acid increases the temperature of 0.150 kilogram of water from 23.9 degrees to 37.5 degrees. Calculate in kilojoule per mole for the enthalpy of combustion of palmitic acid in this experiment. Give your answer to the appropriate number of significant figures. The specific heat capacity of water is 4.18 joule per gram. So, and we want to do this to the appropriate number of significant figures at A level, that is 3. And this is worth 5 marks. So first up, I'm going to use this equation, Q, or you can call it E. E for energy transferred into the water is the mass of the water times the specific heat capacity times the change in temperature. Now, do note at this point that the temperature has gone up. And what does that mean? That means it's an exothermic reaction. It must be releasing heat to the environment. This is important when we get to the final calculation and the 5th mark of this question. You should pause the video at this point, get a pen and write down on scrap paper, see if you can work the answer out. Okay, let's go through it. So Q stands for energy in this case. You can use E if you like. Equals 150 grams. Why grams? Because mass is in grams. So you need to obviously times by 1,000, 0.150, times the specific heat capacity, which is 4.18. And because the specific heat capacity is in grams, it's got G to the -1. That's why we want to convert our mass. If the specific heat capacity was per kilogram, then we would keep it in kg. Now, we're then going to multiply that by the temperature change, and this gives us 8,522.2. 8,527.2 joules. Now, we need to turn it into kilojoules. How do we know this? Look at the unit at the bottom. I've circled it. The unit's in kilojoules. So we've got to divide by 1,000, which will give us 8.5272 kilojoules. So we're only down to like 8 kilojoules now of energy has been transferred into that 150 grams or 0.150 kilogram of water. So this will have picked us up at least 2 marks, possibly 3 at this stage. Now, the answer is kilojoule to the mole to the -1, which means kilojoules divided by moles. So I need to do 8.5272 and divide it by the moles. Now, how do I work out the moles? You know the triangle, mass over mR equals moles. So the mass is 387 milligrams. We need it in grams. Mass is in grams in chemistry. So we're going to do 0.387 because we're going to divide by 1,000 to turn into grams. So 0.387 grams over the MR of palmitic acid. So at this point, you'd have definitely secured 3 marks, but it's quite difficult now. You've got to look at the formula of palmitic acid. See up here, it's CH3, CH2, 14, COOH. You've got to work that out yourself, and it doesn't really give you too much of a hint there, other than the fact that you've been given the mass of palmitic acid. You should work out, I need the moles, because my answer is per mole. So you're going to need to work out the MR. So how do we work out the MR of palmitic acid? Well, what I'm going to need to do is go, well, CH3, that's about 15, 12 for the carbon, 3 for the hydrogens. Then I've got 14 for CH2, 2 hydrogen, 12 for the carbon. I've got times that by 14, so 14 times 14. And then I need COOH, so that's 12 plus 32 for the two O's, and another one, 33 for the, another one for the hydrogen. And you're going to get a total of 256. So then do 0.387 grams, which is the mass, divided by 256, the MR, and that's going to give us 1.512 times 10 to the minus 3, and that's our moles. So now I just need to divide kilojoules by moles. So the hardest bit really was working out the MR of the palmitic acid. You could easily make a mistake there. So, final answer, 5641 kilojoule per mole to the minus 1. But I've just spotted it's 3 significant figures, isn't it? So at A level, we go to 3SF if they ask you for significant figures. So it needs to be 5640. You're only allowed to give 3 numbers that aren't a 0. So, something else I forgot. We need a minus sign. This is exothermic. Remember I pointed out at the start the temperature went up. So you have to have a negative sign with your answer. Okay, moving on, 8.3, state how the value calculated in 8.2 is likely to differ from the data book values. Give one reason other than heat loss for this difference. So, of course, our value is going to be less exothermic. It's lost a lot of heat. When you do calorimetry, you always lose heat through the equipment, through the air, to the surroundings. So you get a less exothermic value. The temperature doesn't go up as much as you think. But we need to give another reason why the temperature doesn't go up as much as you think. And this could be down to something called incomplete combustion. And incomplete combustion releases less energy than when you do complete combustion of a fuel. And so our answer here is incomplete combustion. Superbulous. Okay, let's move on to the next question. Now we have this next one is 8.4. A sample of a different biofuel made from sewage sludge is found to contain 37.08 carbon, 5.15 hydrogen, 24.72 oxygen by mass. The rest of the sample is sulfur. Calculate the empirical little bill. So we're going to go for carbon. We want to do 37.08. We're going to divide that by 12. And then for hydrogen, we want to do 5.15. We're going to divide that by 1. For oxygen, we want to do 24.72. We want to divide that by 16. And then the rest of the sample is sulfur. So in order to work out the sulfur, I need to do 100 minus 37.08 plus 5.15 plus 24.72. And that's going to work out what sulfur is. And it works out at 33.05. And I'm going to divide that by 32. So if you carry this out, you're going to get the first mark. And we're going to get 3.09. We're going to get 5.15, 1.545, and 1.0328, something along those lines. So now I want to divide all by the smallest. Divide all by the smallest. So we want to ratio them. So, and then my answers here, I'm going to do in another color. This is all getting a bit confusing. So this is going to be 3, 5, 1.5, and 1. 3, 5, 1.5, 1. So what I need to do is now multiply to get whole numbers. So I'm going to multiply. Yes, we must multiply. And then we're going to get carbon 6, hydrogen 10, oxygen 3, and sulfur 2. And that is going to get us our, whoops, kind of getting a bit bent there. That's going to get us our 3 marks. Okay, beautiful. Now let's zing off of this. Scroll down, we're on 8.5. Okay, 8.5. Complete combustion of biofuels made from sewage sludge produces greenhouse gas carbon dioxide. Name one other possible environmental problem with the complete combustion of this biofuel. State the formula of the pollutant responsible for this problem. 2 marks. So, we were told that it had sulfur. And of course, the environmental problem is acid rain caused when SO2 dissolves in H2O or reacts. Sod it, I'll put dissolves. The main thing is acid rain. It actually reacts. It's a reaction rather than a physical process. So probably lose myself a mark there. But acid rain, and the formula is SO2, which is formed when sulfur atoms are combusted in O2. S plus O2 goes to SO2. All right, I'm being a bit extra. The only thing you needed to put here was sulfur dioxide. Okay, 2 marks. Beautiful. Right, let's move on. Wasting time. Wasting your time. Right, 3 marks. Holy shamoli. It's a lot of work for 3 marks. So let's have a little butcher's book. So what we're going to do here, holy, right. Ethanol is a biofuel, can be produced by the fermentation of glucose. Glucose is the structural formula shown. Boom, bam. Um, Shows some mean bond and enthalpy values. Boom, boom, boom. Use the equation and the data in table 3 to calculate an approximate value for the enthalpy of fermentation of glucose. For this calculation, you just assume that all the substances are in the gaseous state. 3 marks. Okay, me, myself, and I, baby, me, myself, and I. I find this difficult, so I'm going to draw the displayed formula of glucose, which is a bum. If you're very spatially aware, you don't need to do this, but I am not going to claim that I am spatially aware. I failed my driving test 3 times, so my spatial awareness is bad. Let's go here, peeps. And what we're going to do is zing that there, zing that there. Oh my gosh. I've got issues. Right. Okay, that's a glucose molecule. We need to add up, first of all, how many CH bonds are there? So I've got 1, 2, 3, 4, 5, 6. Hold on. 1, 2, 3, 4, 5, 6. Why have I got 7? I'm missing something. Why did I get 1, 2, 3, 4, 5, 6? Ah, right. So there's 1, 2, 3, 4, 5, 6, 7. So first of all, 7 times 4, 12. Okay. And then what we're going to do, go next to the 3, 4, 8s, and you see you've got 1 there, 2 there, 3 there, 4 there, 5 there. So we're going to go 5 times 3, 4, 8. And then the next thing I want to do is the CO bond. And I've got 1 there, 2 there, 3 there, 4 there, 5 there, 6 there, 7 there. So 7 times 3, 60. And then No, we've got nothing there for the CO bond. We've got the OH bond there. We've got one, two, three, four, five. So 5 times 4, 6, 3. And this is going to give us a total of 9, 4, 5, 9. And that is our bond breaking. And we want to minus our bond making. So now we need to work out the bond making. Um, so I'm going to go over here and draw out ethanol. So we've got two of them. So I'm going to do 2 times all of this. So 1, 2, 3, 4, 5. So I've got 10 times 4, 1, 2. Then I have 1 cc, but 2 times. So I have 2 times 3, 4, 8. I have 1 time, so 2 times 3, 6, 0. And then 1 OH, but 2 times. So 2 times COH, 463. 463. Whack that all together in a calc. That equals 6462. Hold on, we're not finished yet for bond making. Bond making, I've got 2 times this, so carbon dioxide looks like that, but I've got 2 times, so I want 4 times 805, and I want to add that to that, okay? And if we whack those together, we're going to get 9682. So 9459 minus 9682, and that is going to give me minus 223 kilojoule per mole minus 1. And your marks, you're going to get a mark for that, you're going to get a mark for that, and you're going to get a mark for that. 8.7, the carbon dioxide produced from fermentation can be reacted with steam to make more ethanol. The equation for this is blah, 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 blah. Shows some standard of formation. Now, what they've given us here is standard enthalpies of formation. This immediately tells me it's Hess's law. We've got to calculate the enthalpy change. Booyaka Shan. So what I'm going to do here, guys, is I'm going to write this out. 2CO2 plus 3H2O. I'm going to smash that over there to make C2H5 OH plus 3O2. Now, this is just my way of doing it. You don't have to do it like this, but the moment I see that this is formation, I draw 2 arrows going up, one to the reactants, one to the product. So I draw one up to the reactants, one up to the product, and then I look at what elements there are. And you don't really have to do this because unless they ask you to set it out, formation is from the elements in their standard form. So there we go. I'm not going to balance it all up. There's no need. I need 2 carbon dioxide. So I'm going to go 2 times minus 394. There's a reason these arrows are key for me. Some people do this in their head and they don't need them. And then I've got H2O and I've got 3. So I'm going to be 3 times minus 242. And then over on this side, oxygen is 0 in its elemental form. We don't worry about that. But the ethanol is minus 235. Now, what I'm going to do is add all of this together. This makes minus 1514. And over here, that is just that. So that is minus 154. Now, what I do, for Hess's law, I draw a big arrow that goes round like that. And I keep things, if the arrow that I've drawn round from left to right is in alignment with my formation arrow, I keep that number the same. If they clash like this, I'm going to reverse this number here. So this becomes plus 1514 minus 235. And I'm going to get plus 1279. Don't forget to hit the like, write a comment. It helps the YouTube algorithm get more people to my videos, which motivates me more to help you guys out.
You're still here? It's over.